want to make more product, is this an ice bath or a Bunsen burner reaction? Ice bath or Bunsen burner? I'm asking you the same questions in different words. Which one? This has to be a Bunsen burner, right? Why? Because calcium carbonate would just sit there. It's not going to go CO2 on me. I don't have any chalk here, calcium carbonate, until I apply heat. If I warm it up, if I heat it up, then the calcium carbonate will begin to break down into the calcium oxide plus the CO2 gas is going to be. How do I know this? It's because of the 178. Now, like I said, it will always write it down this way. They'll give you the delta H, but you need to be aware, for example, this delta H of minus 297, it actually belongs on this side of the equation, right? 297 kilojoules. If you write it down this way, then you know what to do. 297 kilojoules. That's how much energy, and we can convert the kilojoules to temperature or whatever later. All right, so it really is 297 kilojoules plus the CO2 gas going to form the sulfur plus the O, right? That's what the positive means. The positive means that it actually belongs on the other side. It actually belongs on the other side. The negative in this particular case means that it belongs right here. This is plus. So once again, if I want to make more product, that's what we chemists want to do. We want to make more product. This is definitely not going to be an ice bath situation. This means put the Bunsen burner and heat up that gas, right? Heat up that SO2 gas so it can break down. So the plus and minus tells you where does it go, left or right on the temperature and the heat. If it's on the left side, you apply heat. If it's on the right side, you take away heat to make more product, right? On the other hand, if I said to make less product, then it'd be the opposite. If I don't want to make any calcium hydroxide, I would heat it up and it's not going to make any more calcium hydroxide. Okay, so we write the equations as this, and the solution is going to be plus heat on the first one, right? Plus the heat is going to be on the right side. And the next one, so an increase in temperature will shift the reaction to the left. So so now we do products or reactants, and K will decrease. If it goes more to the left, that means the number in the bottom gets bigger and the number in the top gets smaller. So K is getting smaller. For the next one, the calcium, see where the heat is now? The heat is going to be on the left side. Calcium carbonate sitting there in a flask does nothing until you heat it up, right? It's not going to do anything at room temperature. When you heat it up, then it's going to break down into that. So an increase in temperature will shift the reaction to the right. So CO2 increases, so we're going to increase the gas. And of course, the K value is going to be greater because now the top number is bigger than the bottom number. So yes, K is a bigger number. And then we have, again, it was positive. So anytime it's positive, once again, the heat is on the left side. The heat is on the left side. So therefore, if I want to increase the product, that was my question, I'm going to have to apply heat to it. Got to apply the heat to make it go to the other side. Because if I apply the ice bath, it's not going to go anywhere. It's just going to sit there as a SO2 gas. So an increase in temperature will shift the reaction to the right. So SO2 will decrease and K will increase. Of course, it'll increase. Anytime you put more stuff on the right, the K value is going to get greater. K value is going to get greater. Anytime you shift to the left, the K value is going to get smaller. The K or the Q. Remember, they're interchangeable. But if we're talking equilibrium, we're talking K. We're talking any point in time, we're talking the Q. The Q. So we squared away. Now, the tricky part of this is I asked you, and normally that's a typical question. I want to increase product, right? That's what we chemists want to do. We want to make more products. But sometimes I want the reaction to go the reverse. I want it to go the other way. So remember, that would be the opposite, right? It would be the opposite. If it gives you heat and I put heat, then the reaction is going to go to the left, right? Not going to go to the right. So be aware of that. And certain things, maybe we want them to reverse. You got some disease and you don't want it to progress. You want it to go the other way. Get rid of it. Questions, concerns, test questions on this tomorrow. Add heat and take away heat. Where's the delta H? And I might just use the words too. So remember the words. I may not tell you delta H negative, but I might say it's an exothermic reaction, right? It's an exothermic reaction. It's an endothermic reaction. That's the plus and the minuses on those delta H's. All right. One thing to remember too, the question is always is a catalyst. You guys have heard of catalysts? What are they in the biological world? They're called enzymes, right? They speed up the reaction. So a catalyst speeds up the reaction by lowering its activation energy. Later in the summer, we'll talk about activation energy. A catalyst therefore speeds up the forward and reverse reaction to the same extent. What I want you to know that by adding a catalyst, the K value does not change. The K value does not change. The K will be the same. By adding a catalyst, you'll reach that equilibrium faster. You'll get there faster, but the number for K will be the same with or without a catalyst. It only speeds up the reaction. A lot of folks think that a catalyst shifts the equilibrium left or right. It does not. It will reach the same equilibrium. The only thing a catalyst does is makes it get there a lot quicker than without a catalyst. Okay. Wrote it, write it. All right, here it is. All three things in one slide. It's from the book, guys. You don't have to rush to copy this thing. Open up the book and you'll find this table in the book. And this is it. So, oops. So what happens with concentration? What happens with pressure? What happens with temperature to the reaction? These are the three things we covered. These are three things I expect you to be proficient with tomorrow, for sure. Oh, actually, I should say four. I did cover the catalyst at the end, but the catalyst is just, it's not going to shift the reaction left or right. So increase in reactants, decrease in reactant, it's just the whole table. So go to your book and look at this table and understand this table, and then you got it done. No questions, no concerns? Let's see if we can do this again. Go back and get a real world stuff again. Okay, here's a real world problem, very important problem, the synthesis of ammonia. Ammonia is used all over in industry, and it's via the Haber process. This was actually a German scientist that probably got a Nobel Prize for coming up with this formula to make ammonia. So nitrogen and hydrogen is required, 1 mole, obviously a balanced chemical equation. 1 mole of nitrogen, 3 moles of hydrogen gas will give you 2 moles of the ammonium gas. And it also has a delta H of reaction. The heat of the reaction is going to be minus 196. So there are 3 ways. If you remember the slide before, you know the 3 ways. There are 3 ways to maximize the yield of the ammonia. If I follow the slide, what was the first way? I got to maximize the yield of the ammonia. It means I gotta shift it to the right. I have to shift it to the right. Yell out a few ways to shift it to the right. First way that we covered in the class was what are you gonna do? Concentration. Vary the concentration. We covered a slide where CCl3 and Cl2 or something like that. And you saw it in green and red and move one or the other. So one of the quickest way I can do this is, and this is what we would need. Like I said, we chemists are interested in products. I would remove the product, right? If I remove the ammonia from the reaction, it's going to make more ammonia. It's going to yield more or shift to the right. So by removing the ammonia or decreasing the ammonia concentration, the NH3, taking my product out and go selling it, then this reaction will make more. It will make more ammonia. As long as I don't run out of N2 or H2, it's going to keep making more no matter how much I take. I keep adding more stock solution, more nitrogen, more hydrogen. I keep making more and more ammonia, right? That's one way, by just simply removing the concentration. What about another way? What was the second way we covered? Pressure. All right, what about pressure? Increase the volume, decrease the volume. What's going to make more ammonia in this case? Increase the volume, decrease the volume. What's going to make more ammonia? Anybody? Am I going to make more ammonia if I squeeze it or if I expand it? Remember those rules? Evan, you remember? Are you going to squeeze it? Okay, so if you decrease the volume, you increase the pressure. That's correct. So is that what you want to do? Or you just want to thinking on the fences? I think convince you to do the other one. You what? Sure, you could. Oh man, if I convince you that I would do it, then you talk. Because the rules don't change. Why? Explain to me why you want to increase the pressure or decrease the volume. Okay, because on the left side I've got 4 moles. And 4 moles times 6.023, that's a lot. And then the right side I only got 2. So by squeezing it, by decreasing the volume, increasing the pressure, I'm going to force the 4 to become 2. And I can have still the same pressure with less stuff in there, right? So good, that's the solution. I could also squeeze it down or increase the pressure. If I put this reaction in a vessel and increase the pressure, I will make more ammonia. Okay, so that's the second way. What about the third way? We covered today, the third way. What kind of reaction? What? Temperature. So what do you want to do? Ice bath, Bunsen burner. Ice bath, definitely, right? It's giving you that heat as part of the product. And the question was to increase the product, right? To increase the product. Therefore, if I cool it down, I remove that heat that the reaction gives me. Therefore, it's going to give me more ammonia and I'm making more product, making more product. Simple as that, guys. So decreasing the ammonia by removing the NH3 as it is formed. Yes, that's really the typical process. Decrease the volume, increase the pressure. Sure, I'm going to squeeze the 4 into 2 and I can get more in there. Decrease the temperature, ice bath. There we go. Take the heat away and you got it made, right? Okay. Here's classic examples on this. You can also see the K values. That's the temperature. Look at the K value on this one. 800 hot and the other way. It doesn't want to give you a lot of stuff. Man, you cool it down to 200. Look at the K. It's going to be a lot more product than reactant, right? The top number is bigger than the small number. That's how I get a 7.1 times 10 to the 15th. So an increase in temperature causes the equilibrium to shift towards the reactant since the reaction is an exothermic reaction. And here's an experiment that actually tells you. So the cooler we are, that means remove the heat, 200 K. I get a big K value. It really moves to the right. 800 K, I get a small K value. It doesn't want to move to the right very much. It's an important process. We could also do the atmospheric pressure stuff here. This also would work for that atmospheric. When you squeeze it, you're going to make more. Like industrial conditions, it's circled right there for us.